Welcome, everybody. Welcome to this new seminar of the Reproducibility Basel and the Open Science Seminar. Today, we are joined by Sarah Gibson, who is an open source infrastructure engineer at 2i2c and a contributor to and advocate of open software. She holds more than 2 years of experience as a research engineer at the National Institute for Data Science and Artificial Intelligence, as well as holding a core contributor role in a number of open source projects. Sarah is passionate about working with domain experts to leverage cloud computing in order to accelerate cutting-edge, data-intensive research and disseminating the result in an open, reproducible, and reusable manner. She holds a fellowship with the Software Sustainability Institute and advocates for best software practices in research. And today, she will talk to us about reproducible research and introduction to the Turing way and binder. Thank you very much, Sarah, for joining us. We are really looking forward to your presentation.
Thank you very much. Thank you for having me, and thank you everybody for joining today. So I'm going to talk to you today a bit about my journey through reproducible research and about two projects in particular, the Turing Way and Project Binder. So as mentioned, my name's Sarah Gibson. I'm an open source contributor and advocate. I'm a software and infrastructure engineer as well. I co-lead the Turing Way's infrastructure working group as well, which I'll talk a bit more later on during this talk. And I'm a maintainer of the Jupyter Hub and Binder projects under the Jupyter umbrella. But I just want to give us some context about why I personally care about reproducible research and why we should all care about reproducible research. So in my job, I get asked to fix things a lot. And to be very frank, it's a waste of my time if I can't reproduce the state the project is in to be able to fix what needs to be fixed, instead of like hitting the ground running with what I need, the proper environment, and then I can fix what needs to be fixed. Everybody can go back to building and standing on the shoulders of giants and like building this next layer of scientific output. So yeah, when we can't reproduce what was done before, we spend time trying to figure out, why is this number different? Why is that number different? And we get distracted from the bigger goal, which is advancing knowledge. But also, academic errors have real world effects. There is a lot of errors in the academic literature, and we use this as a base of knowledge of like what it means to be a human, to make decisions about the world. So, for example, this is a spreadsheet here, and that you might be able to see from the quality of the screenshot. There's some countries listed in B column, and there is some numbers listed here, and some of them are highlighted. And this was actually the basis of a financial paper. And the results of this paper actually went into supporting a lot of austerity-based policies that ended up affecting the most vulnerable people in society, including where I am in the UK at the minute. And the eagle-eyed among you may be able to see that this column that is highlighted, not actually all of the numbers in that column are highlighted. And if you redo the calculations with all of those numbers included, you get a very different output that actually does not support any of the austerity policies that were put into place in some of the countries. And this was, the only reason we know about this error is because of this person here, Thomas Herndon. He is now a faculty member at Stanford, but when he was a PhD student in economics, he had to, as part of his coursework, reproduce the findings of a published paper. And he asked Reinhardt and Rogoff, who were the publishers of the initial paper and results for their data. And he was the one who found out that when they were doing their calculations, they had just missed off the last 5 countries. And when you do reanalyze the data, you get a different result. And all of this is to say that if you take nothing else away from my talk today, take this. It's that I'll be talking a lot about technology today, but actually the hardest part about reproducibility is human beings. We don't have the incentive structures, and that makes it very difficult to want to show that you made a mistake. So well done to Reinhardt and Rogoff for sharing their data when they were asked, but they didn't then retract the paper when it was found out that there was a mistake. So I think that speaks a lot to the culture of reproducibility within academia at the moment. But I want to talk to you today about the Turing way and binder I'm going to frame it as a timeline, as a walk through my career, actually, because the Turing way in particular is like very tied to my career. I can't give a careers talk without mentioning the Turing way, and similarly, I can't give a Turing way talk without mentioning without talking about how it impacted my career. So the timeline we're going to be like walking through is my career, and we'll be jumping around different parts of the project and binder and what I'm doing now as well as we go along. So back in late 2019, I finished my PhD, and I have a PhD in astrophysics, and I studied gamma ray bursts and X-ray astronomy. So the instrument I was using was orbiting Earth, which kind of defaults you into becoming a software engineer and a programmer. So I've been running a lot of computer code and modeling. And when I started looking for a job, I decided I didn't want to stay in academia anymore. But the experience I had stood me in good stead to get a job at the Alan Turing Institute, which is the UK's National Institute for Data Science and Artificial Intelligence. And I was successful in getting a job in the research engineering group there. And I was hearing about this new project that was going to get kicked off. And they were talking about all of the skills needed for reproducible research. So probably a lot of folks in the room right now are familiar with a lot of the barriers on reproducible research. It's not that, as I mentioned before, it's not that we don't want to, but like the incentive structures are not there to permit us to do reproducible research. My favorite one on here, by the way, is plead the fifth, which comes from the American like legal system. And it's related to what I said before, like, why would anybody want to give evidence against themselves? We know there are errors in the literature. Why would anybody put their head above the parapet and say, I made a mistake? And this is why I think it's really important that we try and build a world where it's okay to be human and make mistakes, because fraud isn't our biggest problem, just that we don't have those incentive structures to actually have our work thoroughly checked by ourselves and others. But the two barriers that we were focusing on back in 2018, 2019 at the start of the Turing way, where it takes time and requires additional skills. So people think reproducible research takes time to like set up. And that is true if you're only thinking about a short concept of success, if you're only thinking about getting that next paper out. But if you can automate some steps, get your analysis to run reliably over and over again, you can be much more successful in the long run because you can move so much faster. But it does take a little bit of time, and you need to learn some additional skills. And the Turing way was born from this idea of helping people learn those additional skills so that it can move that little bit faster in the direction of reproducible research. So this was how the Turing way was born. It was a lightly opinionated guide to reproducible data science. And it wanted to provide all the information that researchers need at the start of their projects to ensure that they're easy to reproduce at the end, which also meant that everybody involved in producing the research, from PhD students all the way up to funding teams, knew which part of the responsibility of reproducibility they could affect. And some of the initial topics that came up were version control. Version control is like pretty much a prerequisite for everything in the Turing way, because if you can get people onto version control systems, then everything else flows quite easily. It is that answer to that age-old question of, but this worked last Tuesday, what has changed? It's there in your version control history. So that was like the first thing we wanted to get people onboarded onto. The next topic was testing. We all know that testing is important, but I'm not sure that much academic code is formally tested. I know that academics are doing tests as we work. We call them sanity checks. We plot graphs and distributions and make sure that everything looks like it makes sense. But I think that some folks are not sure how to programmatically do that so that those tests can be run automatically. And like testing doesn't have to be complicated, but it is just really valuable to be continually checking your code and checking that it's doing what you think it's doing and adding a test before you change anything, just so that everything still makes sense and we're still on the right track. It's the hardest part I've experienced as an engineer is people sending us quote unquote better versions of their code. And they are definitely better. They fit the data better, but they're not reproducible in terms of what was tested and what was published. So, and continuously testing in this way makes you be more explicit about what has changed. It's fine to update a broken test. You're just being explicit about like, why did that test break? Is it because the science you were testing changed? And that's totally fine. So another concept we wanted to teach people about was continuous analysis and continuous integration. This is the idea that code changes are tested for correctness by automatic tools before being integrated into the project. And this like fits really well with the scientific method as we are taught it's supposed to be, but maybe not the way that it is instantiated in the way that we do our work currently. But yeah, you start by planning and designing your experiment, and then you write those steps down in code, and you push it to version control and run your analyses. And I want to point out here that you can put your data up on a public server, and that there are a lot of tools that can help you do that and run your analyses automatically that way. But you don't need to make your data public in order to follow this process. The important part is that all the steps are run every time you make a change, and you test to see what's changed. And then you can get really excited because it feels so good to be validated in a job that doesn't validate us most of the time, when all of your tests pass and your change has worked. So yeah, just to reiterate that, you should be running your complete analyses repeatedly, like as you work, as much as possible. And as I said before, a lot of the time your tests will fail, and that's fine, because you're developing your analysis and you're learning as you're going, and you're improving incrementally as the scientific method, as we're taught, expects us to do. But yes, as you break things, you'll be explicit in how you're fixing them and why you're getting a different result or not. So the big example here that motivates people is when you're writing academic papers, you work for 6 months on figure 1, you show it to your collaborators and they say, that's great. And then you work for 3 months on figure 2 and another couple of months on figure 3. And like, I'm definitely guilty of this. By the time you're running your code to produce figure 3, you're no longer getting the same output for figures 1 or 2. So I'm just advocating for that check and being explicit about your changes all of the time. Another topic we wanted to cover in the Turing Way was the idea of the FAIR principles. This stands for findable, accessible, interoperable, and reusable. The idea that your data sets are explained and easily adopted to other purposes. And these are designed for data, though there are working groups who are trying to apply these principles to software and other types of outputs as well. And again, I want to point out here that making your research fair doesn't mean that it has to be open. A lot of people think when we say accessible here, we actually mean public data sets, and that's not strictly true. It's totally fine to work with private data or code, but it doesn't. What we are asking for is that the process by which someone new could join the project and get access to the data, that process is open and accessible and findable. And yeah, as the image here says, there's a meaningful interaction that can unlock you into accessing that data, but it does not have to be public. So I, starting at the Turing Institute, thought, this is amazing. These are all the skills I need to know to do my job well, this brand new shiny job that I've got that I don't understand, because I actually did not know anything about version control when I joined the Turing Institute back in 2018. I'd never used it before. I remember on day one, my boss asking me for my GitHub handle, and I was like, Git what? I was like so excited to find this project where we'd be documenting the basic tools that I felt like I needed, and I was really keen to get started work. And then Kirsty Whitaker, the founder PI of the project, she was like, that's great, but I have another plan for you, Sarah. And that's because there's another part of reproducible research that is like really, really hard that I haven't mentioned yet, and that is sharing a software environment. And if you've ever been trying to run someone else's code and you've heard them say, oh, well, it works on my machine, and you felt that anger at such an unhelpful statement, you will understand how difficult it is to share a software environment. And that is where I was introduced to Project Binder. This is actually the Binder logo. I realized my geometric shape presentation slides might make you just think this is a pretty thing, but no, this is actually the Binder logo. And I'm going to give you a live demonstration right now. They always say never do live demonstrations, but I'm going to do it. So what this is a Binder link, and it's going to load up and take me to a Jupyter notebook. And we are going to analyze some gravitational waves. I mentioned I've got a PhD in astrophysics, and I wasn't going to let y'all get away without some astro stuff today. So this is, this Binder working away in the background. Eagle-eyed among you might notice words like container and such. And then we spin out, open up Jupyter Lab, and a notebook gets open, which is the binary black hole signals into the LIGO open data, the LIGO being the Laser Interferometric Gravitational Wave Observatory. And I can click run all cells here. And we can let this run, and we can see some data from the LIGO experiment. So we can see a couple of strain graphs here, which shows the changing lengths of the two arms of the interferometer. We can see the, so this is as the two black holes spiral into one another and merge as they ring up. This is their strain data. And a nice contour plot of the strain data. And here's again that they call this the chirp. This is at the moment of merge. The frequency increases. And again here, you see the chirp. And this side here is called the ring down, as the object that is formed from the two black hole binary, from the merger, settles, it kind of like resonates a little bit, and that's called a ring down. And there's actually the chirp sound, they've shifted it into the human hearing range as well. So I think there's an audio clip in this notebook here as well. But I'm getting too deep into astrophysics here. And the point is that all I did was click that link, and I got access to all of this interactive stuff, learning about black holes, playing around with data. I could change something if I wanted to and rerun this, and the date and like the results would update with my change. And all I did was click a link, and that is the beauty of Binder. So here's like the workflow in cartoon form that a researcher would go through to use Binder. So we have Jane up here, and they've written a paper based on their experiments. And she would like anyone to be able to reproduce, check, and improve her calculations. So what she does is she describes her experiments as a Gibson notebook using prose, code, visualization, and she adds extra resources such as source code, the data, any media. She publishes them publicly on a publicly hosted repository such as GitHub, Bitbucket, GitLab. And then she makes that repository binder ready by describing the software required to run the notebook. So she includes a configuration file along with everything else. And configuration file here really is as simple as, if you're using Python, it could be a requirements.txt file that gets pip installed. If you're using R, it could be a description file. If you're using Julia, there's a TOML file. Basically, whatever ecosystem you're using to install your environment, Binder should be able to recognize it. And then something down here happens, and Jane gets a link out, which means she can now share that link with anyone around the world, and anyone can run and reproduce her computations. So that little icon down there is actually doing quite a lot of work because that is the actual tech stack, which we call Binder Hub. And Binder Hub, as a piece of software, allows you to coordinate cloud computing resources with Kubernetes. Everything I was showing you in that Jupyter notebook was running in the cloud. It was not running on my local machine. And it makes it easy for users to access via a Jupyter Hub. Like it's all browser based. There's no specific software or APIs or CLIs you need to access it. And you can very easily set up your environment from your GitHub repository. So this is like a little snapshot of the form you get if you go to mybinder.org and you put in the URL of the repository you want to build, and you click launch. And the first thing that happens is your repository is cloned using a very basic Git process. We then have an open source tool called Repo2Docker that builds a container image according to those instructions within your repository. So that's when your configuration file gets read and executed. We then run that container image with Docker. We have a Jupyter Hub running under the hood, and its job is to allocate computational resources. So it will go to the cloud, whatever cloud it's deployed on, and ask for a certain amount of CPU and RAM. And the next thing it does is make that running container backed by cloud compute resources available via some URL. And then the last binder layer just redirects your browser to your URL with your running infrastructure ready to do some work, which is all very cool. And just Binder really helps with the mindset of reproducibility. This is why we included it as a project in the Turing way, because to use Binder, you need to have a lot of the things that are required of reproducibility, because you need to use version control, because it's doing a git clone, it's looking for a version controlled repository. You need to describe the software environment. It needs that configuration file so it knows what to build. And if you push a change to your GitHub repository or whatever repository you're using, Binder will automatically rebuild it. So you get that continuous integration, continuous analysis field where you get a new build for each change. It also makes that sharing responsibility we talked about earlier super easy. It really smooths the path because you just get that URL that you can share and people are automatically like placed into that environment. And because the compute is coming from the cloud, not your local machine, it means that you can actually run analyses from your phone. I did a Binder workshop once actually at a place where I couldn't get onto the Wi-Fi network. So I was tethering from my phone. And yeah, because everything was happening in the cloud, I barely used any data because all my phone was seeing was just a browser refresh and not actually all of the build stuff that was happening in the back end. And like ultimately, it just feels fun to use. It feels fun to set up your software to get it working in Binder whilst actually making computations like more accessible to more people. So this is why we're a fan of Binder. But I've talked about mybinder.org so far, which is the public instance of the Binder software. But because it is an open source project and the whole tech stack is open source, Kubernetes at like the infrastructure layer is an open source project, as is Repo to Docker and Binder. That means you can run your own Binder hub. And you might want to do this because you might want more computational power than the public version at mybinder.org gives you. Maybe you want to give people access to GPUs or stuff like that. And you might also want to limit who has access, which I've kind of like represented here with this little house instead of the globe. Like maybe you only want to share in a certain group of people. And this is exactly what my job on the Turing way in the early days at the Turing Institute was. I built like a Turing flavored Binder hub and provided a Binder service that was only accessible to members of the Alan Turing Institute at the time. So it's like a reproducible piece of software, basically. And also because the tech stack is completely open source and including the config for mybinder.org itself is stored in an open public repository on GitHub. It means others can run their own Binder hubs to specifically support the mybinder.org service. All this is to say mybinder.org itself is federated. So there's not just one cloud cluster running this whole thing, but multiple spread around the world and actually on different cloud providers. So the GKE was Google, Turing was running on Azure, Giesis was running on bare metal actually, and OVH is another European cloud as well. So all of these running on like different infrastructure, but from the user perspective, it was one browser, it was one seamless experience. And this is important because mybinder.org is a free to use service and therefore depends on grants and support from cloud providers to operate. But more hubs means that mybinder.org's existence is less reliant on a single grant. So for example, if Google decided to no longer support this cluster in the US, mybinder.org wouldn't disappear because there's still 3 hubs supporting the service. And actually this happened a couple of years ago. Google stopped supporting mybinder.org and the Turing stopped supporting the instance I set up at the Turing a few years ago as well. But we also received additional support from and resources from KervNote to add another federation member. So thank you to these folks for helping us keep mybinder.org up and running and available for folks to use. Back to the Turing way. I've skipped forward to the present day at the minute because I want to talk about the growth of Turing way from those early days when I was tinkering with Binder and learning version control and Kubernetes at the same time, which, by the way, was a roller coaster, to where we are now. So project has been running for 5 years. We've got over 500 contributors, over 5,000 monthly visitors, more than 350 chapters in the book itself. And the Turing Way also got a lot of recognitions, supported by over 25 core members, mainly through governance, won 2 awards and has engagement with more than 45 different organizations, been referenced in more than 40 peer-reviewed articles and hundreds of publications and reports and policy documents, including in the UK government and the health sector as well. And it's also been replicated and extended by 3 projects that were internal to the Turing Institute and more than 7 external projects as well. This has been like a huge jump in growth, and I kind of want to take us back now, what we learned from that during that growth spurt was that doing good data science takes more than just open and reproducible practices. We were learning that as our community grew, as we were introducing new voices and perspectives, people didn't want to just talk about reproducibility. Like, that's not the be an end all for gold star research, as we called it. So it's also things like how we communicate our work with others, how we design our projects, and how we efficiently collaborate with each other. And how do we consider the ethics and integrity of our work? So back in 2020, we took the idea to expand the Turing Way and add 4 new guides alongside the original guide to reproducibility, and also added a community handbook. We wanted to help people build the foundational skill sets to include these extra parts of data science that we'd discovered during our growth. And we also wanted to make sure that the Turing Way could continue to be reproduced across different communities. So we maintained the community handbook that compiles all of our processes and community practices into one place so that it can be reused and re-implemented by others. One thing we brought into around this point as well was the idea of a working group. So these are like self-organized groups collaborating and co-creating together on different topics and tasks which fit into the interests and skills of the group of the people, but also pushing forward the Turing Way's mission. And anyone can join one of these groups, and the focus is on like empowering community members to steward different aspects of the project. So as you can see, we've got quite a few different groups around here. And yeah, the infrastructure maintainers working group is where I sit, and I'll talk a little bit about what that means and how we're thinking about reproducibility there. So yeah, I co-lead the infrastructure working group with a few other members, and our main job is to just try and keep the lights on and keep the Turing Way book accessible and on the internet and building properly. But we're also interested in cross-platform reproducible builds. So you should, if you want to, you should be able to build the book locally, and you should have the same experience whether you're running on Mac, Linux, Windows. But to that end, we also care about portability across hosting infrastructure as well. So at the minute, the book is currently hosted on Netlify. We're doing works to move us away from that platform. And as these different hosting providers come and go, wax and wane, we want it to be very easy to move the book across these platforms with as little disruption and as little extra effort as possible. And the way to do that is these reproducible builds. So some notable efforts the infrastructure team have been involved in. We now have a dedicated URL for the book. We were using the raw Netlify URL before, and we argued that from a perspective of we wanted to prevent link rot. If you go into the Turing Way annals of Zenodo and previous talks, you'll see all of these Netlify links. But if we swap platforms, all those links will die and they'll all break. And yeah, that doesn't help us with link rot. So having a URL allows us to move the book across infrastructure without breaking things and also allows us to move with minimal downtime because swapping the URL over will be the last thing that we do. Another thing we've got is a dedicated GitHub organization. We were previously housed within the Alan Turing Institute's GitHub organization, but that restricted us in terms of who we could give like certain GitHub admin rights to. Generally, they needed to be a staff member of the Turing Institute. So having our own GitHub organization allows us to be more freely delegate power and responsibility to our community members, particularly if they don't work for the Turing Institute. This also means we can split the repository up. If you've ever visited the Turing Way repository, you'll see that it was a giant monorepo, and that was partly because we were within the Alan Turing Institute's GitHub organization. But now we're aiming towards a separate place for the book itself, for meeting notes, for workshop resources, and hopefully that will make things a bit more navigable in terms of it's not just a bunch of folders, but actually things are a bit more separate and structured better. But the big thing we are trying to move towards is supporting multilingual builds of the book. The localization and translation working group have done a seriously amazing job of like honing down the translation process and getting the book translated into different languages. By the minute, we don't have a system for hosting these translations in a reproducible and portable way. So that's why we're interested on like moving platforms and making sure that we build a robust system to get these translations online in the most sustainable and maintainable way possible. So this is like a slightly different aspect of reproducibility and like how we think in the Turing way. So skipping forward a little bit back to 2021, I start a new job. I'm still involved in the Turing way to this day. That hasn't changed, but I leave the Alan Turing Institute and I get a job in a startup, and I'm moving more deeply into infrastructure and the open source world, and we're particularly interested in like reusing existing tools to create an improved open science experience. So I moved to ITC, the International Interactive Computing Collaboration, which is a non-profit startup, and we aim to grow a global network of community hubs for interactive learning and discovery. So the idea for this startup came out of like a key need in open science. Like on one side, we have open source communities who are building the tools that go into doing data science and research, and they need support developing the infrastructure to like run their tool set and their ecosystem on. And then on the other side, we have these scientific communities who are trying to benefit from these open source ecosystems to run reproducible open science, but they need support deploying the infrastructure. And the idea is like 2ITC kind of like sits in the middle here as this feedback loop where we deploy and manage the infrastructure on behalf of these scientific communities and help them use open tools to figure out their workflows, and we gather feedback and we use that feedback to help the open source communities that are creating the tools develop what they need to develop and do that in a sustainable way. So to just look into that cycle a little bit more closely, we've got like these building blocks from an open ecosystem of different tools and data and infrastructure. And we work with our community leaders to design workflows around their knowledge creation and needs in a community hub. And we manage that infrastructure for a global network across many domains, which means we really get the breadth of how these tools are being used in all different kinds of research. And we can take that back. And we're not just like dumping feedback either, we're working upstream as well to improve the ecosystem of tools on behalf of the communities, so that when we start the cycle again, this pool of open building blocks has been enriched, right? And Jupyter is a core part of the open source building blocks that we draw from, where Jupyter is an open community dedicated to modular and platform agnostic tools for interactive computing. And its principles for developments are that we do build those modular, composable, and customizable tools so that everything should work together and you can build out the workflow that is needed for that community. It's to create and support the open standards and protocols so that we can interoperate even outside of Jupyter ecosystem, with that focus on that interactive computing workflows that you saw a brief glimpse of with the binder link, so that we can prioritize exploration of data, rapid feedback, and like rapid development, and throwing bits of code together and then like communicating those ideas rapidly as well. At the minute, we've got a global network of over 100 community hubs across 5 continents. And that's super key for getting the kind of feedback and user stories we need to like build out these workflows. And I'm really proud that we've got a decent amount of representation. Could always be improved, but a decent amount of representation in the global south in the form of Latin America and Africa as well, because it's really important that the voices of the researchers doing work in those areas is lifted up. And all of this is to say that when we connect these hubs together of people, the co-creation that comes out of that is science's superpower. That's how we're going to push forward the boundaries of knowledge, because when you explore together and develop together and discover together, yeah, that's when you make the breakthroughs. And it's also a more enjoyable way to exist in academia, in my opinion, as well. But like just highlighting this bit here, sharing new ideas in a way that others can reuse, reproduce, and improve. That's coming back to that binder workflow, where you can very quickly share a link with someone. They're in the environment, they can see what's doing, they can play around with it, they can reuse it, reproduce it, improve it, and rapidly give feedback. And we are deploying binders as well. We're running Jupyter hubs in the background. And this leads into another way that we think about reproducibility into ITC specifically, and that is our right to replicate. So this is reproducibility of the infrastructure you are running on. Our right to replicate gives communities the right to move their infrastructure in its entirety elsewhere, with or without to I2C. So one of the big things we're trying to tackle is vendor lock-in. You can get a lot of these managed hub services directly from cloud providers, but you end up locked in with your data trap there. Your workflows don't work anywhere else. Whereas to ITC make a commitment that we build using open source vendor agnostic tools from the bottom up, so that we can very easily port across different cloud providers. And we do run hubs across all 3 major cloud providers, as you saw with the mybinder.org federation as well. So yeah, you see, must be open source, must be portable. All of these considerations we're now thinking about at like the level of the machine that is running, as close as possible. Eventually, you're always reliant on someone else's machine. So yeah, that is my career story through reproducibility via the Turing Way and Binder and so I2C. Thank you very much for your attention, and I will be very happy to take questions. Thank you very much.